If you could somehow scoop a single teaspoon of material from the crust of a neutron star and bring it to our planet, you would be holding something that weighs approximately 1 billion tons. This is the equivalent mass of a mountain compressed into a volume no larger than a sugar cube. The sheer physical presence of this material on Earth would not just be a scientific curiosity. It would trigger a release of energy comparable to an extinction-level event. To understand what happens when a drop of this exotic matter touches our surface, we first have to look at the violent environment that creates it. Neutron stars are the collapsed remnants of massive stars that have exhausted their nuclear fuel. When a star significantly larger than our Sun runs out of energy, its core collapses under its own gravity with such force that it crushes atoms into a dense soup of subatomic particles. Electrons and protons are smashed together to form neutrons, creating a sphere roughly the size of a city, but with a gravitational pull so strong it warps the path of light. This density is the key to why a single drop is so dangerous. On the surface of a neutron star, gravity is 200 billion times stronger than on Earth. The material is held in this hyper-compressed state only by that crushing external pressure. The moment you remove a drop from that environment and place it in Earth's atmosphere, the internal pressure of the degenerate matter is no longer balanced. It is like a spring that has been compressed by 1 trillion pounds of force suddenly being released. The instant this drop appears on Earth, it is no longer bound by the extreme gravity of its parent star. According to the Pauli exclusion principle, two identical fermions cannot occupy the same quantum state. In a neutron star, the neutrons are packed so tightly that they are fighting for space, creating what we call neutron degeneracy pressure. This pressure is the only thing preventing the star from collapsing further into a black hole. When that drop hits our atmosphere, that internal pressure becomes an outward explosion of unfathomable proportions, because there is no longer any massive gravity to hold the neutrons together. They will undergo beta decay. A free neutron is unstable outside of an atomic nucleus. With a half-life of about 10 minutes, it decays into a proton, an electron, and an antineutrino. This process releases a significant amount of energy per particle. Given that your single drop contains roughly 10 to the 30th power neutrons, the total energy release is catastrophic. This isn't just a chemical explosion or even a standard nuclear fission event. It is the sudden expansion of the densest non-black hole matter in the universe into a volume millions of times larger. As the drop touches the ground, it wouldn't just sit there like a heavy rock. It would immediately sink. Earth's crust is made of silicate rocks and metals that are essentially empty space compared to the density of a neutron star. To the drop, the ground would offer no more resistance than a cloud of steam offers to a falling lead weight. It would punch through the sidewalk, the bedrock, and the mantle, accelerating toward the center of the Earth. However, it wouldn't get very far before the expansion phase takes over. Within microseconds of arriving, the drop would expand from the size of a raindrop to a sphere of plasma hundreds of meters wide. The energy released would be roughly equivalent to 200 quadrillion joules. To put that in perspective, the largest nuclear weapon ever detonated, the Tsar Bomba, released about 210 petajoules. A single drop of neutron star material would effectively be a multi-megaton thermal punch delivered directly into the Earth's crust. The resulting shockwave would flatten every building within a 50-mile radius and create an earthquake felt across the entire tectonic plate. The heat generated during this expansion would be hotter than the core of the sun. At the point of contact, the air itself would turn into a blindingly bright fireball of X-rays and gamma radiation. Any biological life within the immediate vicinity would be vaporized before their nerves could register the pain. The atmosphere would be pushed outward so violently that it would create a vacuum in the center of the explosion, followed by a secondary sonic boom as the air rushes back in. If the drop were placed on a ship in the middle of the ocean, the water would flash steam instantly, creating a localized tsunami and a pillar of steam that would reach the stratosphere. But the physical destruction is only part of the story. The radioactive fallout would be a global concern. Because the neutrons are decaying into protons and electrons, you are essentially creating a massive cloud of hydrogen plasma that is highly radioactive due to the flux of neutrinos and the secondary reactions with the surrounding nitrogen and oxygen in the air. This would create isotopes that don't normally exist in our environment, poisoning the atmosphere for years to come. We must also consider the gravitational effect of having 1 billion tons suddenly appear at a single point on the surface. While the Earth itself weighs 6 sextillion tons, having 1 billion tons concentrated in a few millimeters would create a localized gravitational field. If you were standing 10 meters away, you would be pulled toward the drop with the force of a high-speed car crash. This tidal force would be brief because the drop would expand so rapidly. But for the first few milliseconds, physics would break in your immediate vicinity. The ground around the drop would be sucked inward before being blown outward by the thermal expansion. It is a paradox of physics, a substance that is both a gravitational sinkhole and a high-explosive bomb. This helps explain why neutron stars are so stable in space, but so volatile if moved. The star's own mass provides the containment vessel. On Earth, we have no container strong enough to hold it. Even if we tried to use magnetic fields, the strength required would be millions of times greater than our most powerful superconducting magnets. The material would simply shred through any magnetic bottle we could build. There is also the matter of what kind of neutron star material we are talking about. Most people imagine the core, which is the densest part, but the crust of a neutron star is actually a solid lattice of nuclei, mostly iron, submerged in a sea of electrons. Even this lighter material is still millions of times denser than anything on Earth. If we took a drop from the outer crust, the explosion might be slightly less energetic because the degeneracy pressure isn't quite as high, but it would still be enough to delete a major city from the map. If we took the material from the inner core, where things like quark-gluon plasma might exist, the physics becomes even more speculative and dangerous. In the core, the pressure is so high that individual neutrons might dissolve into their constituent quarks. Removing that pressure could lead to a phase transition that releases even more energy than simple neutron decay. We are talking about the basic building blocks of matter rearranged into their most compact form, suddenly being given the freedom to stretch out. It's like taking a skyscraper-sized piece of foam and compressing it into a grain of sand, then letting go. One of the most fascinating aspects of this scenario is the speed at which it happens. When we talk about geological or astronomical events, we usually think in terms of millions of years. This happens in the time it takes for a photon to cross a room. The conversion from a drop of matter to a continent-shaking explosion is nearly instantaneous because the forces involved are the fundamental strong and weak nuclear forces, which operate much faster than chemical bonds. There is no slow burn with a neutron star drop. This reality highlights how fragile our environment is compared to the extremes of the universe. We live in a low-density, low-gravity pocket of the cosmos. Our chemistry, our biology, and our engineering are all based on the behavior of atoms that are mostly empty space. A neutron star is the ultimate proof that matter can exist in a state where that empty space is removed. If the universe were a sponge, Earth is the air-filled foam, and a neutron star is the solid rock. Bringing the two together is an exercise in violent displacement. From a planetary perspective, a single drop wouldn't destroy the Earth entirely. The planet has survived impacts from asteroids that were miles wide and traveling at tens of thousands of miles per hour, while the energy release of our neutron star drop is comparable to a massive asteroid. It is concentrated in an incredibly small area. The Earth would sustain a massive crater, perhaps several miles deep, and the global climate would be pushed into an impact winter due to the dust and debris kicked into the atmosphere. The planet would remain in its orbit, and life in the deep oceans or on the other side of the planet might survive the initial shock. The real danger would be if we brought a significant amount, like a kilometer-sized chunk. At that point, the mass of the neutron star material would be enough to physically pull the Earth toward it, potentially shredding the planet through tidal forces before the material even touched the atmosphere. A single drop is a disaster for civilization. A kilo of the stuff is a disaster for the solar system. There is also the question of how the drop would look in the split second before it detonated. Because of the extreme density, it would likely be perfectly spherical and incredibly shiny, as it would reflect and refract light in ways that no earthly material can. It would look like a small silver bead, but it would be so heavy that it would appear to be welded to the spot it occupies if it were sitting on a table. The table wouldn't just break. The atoms of the table would be crushed into a plasma as the drop's gravity pulled them in. In fact, before the drop even touches the surface, it would be pulling air molecules toward it so fast that they would undergo nuclear fusion on its surface. As the drop falls through our atmosphere, it would be surrounded by a continuous streak of fusion fire, looking like a miniature sun falling to Earth by the time it actually reached the ground. The drop would already be the center of a massive column of ionizing radiation. This thought experiment serves as a reminder of the scale of the universe. We often think of space as a vacuum, nothingness, punctuated by stars. But those stars are factories of unimaginable physical conditions. A neutron star is essentially a single atomic nucleus, the size of Manhattan. It represents the limit of what matter can be before it ceases to be matter at all and becomes a singularity. By imagining a drop of this material on Earth, we are bridging the gap between our human-scale reality and the high-energy physics of the cosmos. It shows us that solid ground is an illusion created by the electrostatic repulsion of atoms, and that under the right conditions, that solid ground is as soft as tissue paper. We are lucky to live in a part of the universe where matter is spread thin. If the density of the universe were just a little higher, the stability required for chemistry and life would likely be impossible. Our existence depends on the fact that these extreme objects stay far away from us. Even the most advanced hypothetical technology could not safely handle this material. To keep a drop of neutron star matter stable on Earth, you would need to generate a gravitational field equal to that of a star within a space the size of a room. If you could do that, you would have created a gravitational well so deep that it would pull the rest of the Earth into it anyway. There is no winning move when dealing with the remnants of a supernova. The sheer density dictates the terms of the interaction. While we can study neutron stars from thousands of light years away using X-ray telescopes and gravitational wave detectors like LIGO, we are strictly forbidden by the laws of thermodynamics and gravity from ever touching them. The data we gather from these stars tells us about the origin of heavy elements like gold and platinum, which are created during neutron star collisions. In a way, we already have bits of neutron stars in our jewelry and electronics. The atoms themselves were forged in these violent environments, but the concentrated, raw material is a different beast entirely. It is the purest form of power in the cosmos. And even a single drop is enough to remind us of our tiny place in the grand scheme. Ultimately, the arrival of a neutron star drop would be the ultimate test of Earth's resilience. It would be a localized apocalypse, a blinding light, and a geological scar that would take millions of years to heal. It teaches us that the laws of physics are not just abstract equations in a textbook. They are the rules that prevent our world from collapsing or exploding at any given moment. We thrive in the low-energy suburbs of the galaxy, far from the white-hot, high-pressure centers of dead stars. The next time you look at a mountain, remember that a piece of matter no bigger than a marble could outweigh it. And the next time you feel the ground beneath your feet, remember how relatively empty it truly is. The universe is a place of extremes, and we are fortunate to live in the middle. If you found this exploration of cosmic physics fascinating, consider how much more there is to learn about the strange objects lurking in the dark between the stars. Understanding the universe's most extremes helps us appreciate the delicate balance of our own world. What if you could take a single teaspoon of a neutron star and bring it to Earth? This thought experiment explores the terrifying physics of the densest matter in the universe. We break down the science of neutron degeneracy pressure, gravitational tidal forces, and the catastrophic energy release that would occur the moment this exotic material leaves its high-gravity home.